Hi guys, this is Mrs. DeBella teaching you from home. We're going to do all of the lessons this way until I return. YouTube videos, and we'll go section by section, just as if I were in class. Right now we are starting a brand new chapter. We are in 4.1. Probability distributions is the name of this section, and it starts off rather simply, thank goodness, okay? The first thing that we are looking at in example 1 is being able to determine the difference between discrete and continuous variables. Now, discrete means it is an exact number, okay? Like the number of days in a week you go to school, 5 days, that is discrete. Continuous would be, say, the number of minutes it takes you to get from your house to school, okay? That could be 10 minutes and 24 seconds, okay? Definitely not discrete. So example 1, it says determine whether the random variable x is discrete or continuous. So in the try it yourself 1, the speed of a rocket is number 1. Number 2, the number of calves born on a farm in 1 year. Well, obviously, you know from number 1, the speed of a rocket does not have to be a specific constant whole number, okay? Therefore, it is a continuous random variable, whereas the number of calves born on a farm in a year is a discrete number, 1, 2, 3, 10, 20, etc. Easy enough, okay? Now, moving down a little bit, we are looking at discrete probability distributions, okay? So we're going to be using this for constructing discrete probability distributions and then making histograms from that. So the probability of each value of the discrete random variable is between 0 and 1. That is a rule, okay? So the first rule is that the probability, the sum of all of that, well, let's see. The probability has to be between 0 and 1. That is the first condition. And then what we see is that the sum of that probability has to equal 1. If these two rules are not followed, we do not have a discrete probability distribution. Okay, so if we look at example 2, okay, it says constructing and graphing a discrete probability distribution. An industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a score from 1 to 5, where 1 is extremely passive and 5 is extremely aggressive. A score of 3 indicated neither trait. The results are shown at the left. Construct a probability distribution for the random variable x, then graph the distribution using a histogram. Okay, so obviously, here's what we've got. We've got the score, which is x, and that is 1, 2, 3, 4, 5. That is your level of passive-aggressive from 1 to 5, where 3 is neither trait. Then you've got the frequency, okay? So we need to first determine whether or not this is actually a discrete probability distribution, okay? So we've got 24, 33, 42, 30, and 21. Now, what we need to do with that is we are going to figure out the relative frequency, okay? But in order to do that, we need to know the total number. So let's just check this. 24 plus 33, 42, 30, and 21. That gives us the 150 people that we were told were given this personality test. Okay, so that adds up. So what we're going to do is find the relative frequency for each one of these things. Okay, and remember, in order to do that, what we do is we are going to divide the frequency by the total. So 24 divided by 150. 33 divided by 150, etc. Okay? So this is what we're going to do all the way down the line. Find the relative frequency of each one of these entries. Okay, so 24 divided by the 150, we get 0.16. These numbers are what's important as far as following those two rules that we need to follow to determine if this is actually a discrete probability distribution or not. We need these relative frequencies. Okay, so working our calculators. Keep in mind as I'm going through this, you will also be working your calculator so you understand where these numbers are coming from and you can replicate this process. Okay, there's our relative frequency. Now, all of them are between 0 and 1. So that is the first rule that's followed. Yes, all the relative frequencies are between 0 and 1. Now let's add them up. 0.16, 0.22, 0.28, 0.20, 0.14. If we add those up and we get a 1, that follows the second rule. The sum of all of those relative frequencies is equal to 1. So this is a discrete probability distribution. So we could then make the table from that. So we know that histograms, we have the relative frequency along the y-axis, okay? And the score is going to be down here, okay? And this is the probability, which is our decimals there, okay? So we can go up by 0.5, so 5, 10, 15, 20, 25, and 30. Okay, so all of the decimals that we've got over here fall in our probability scale. So the score, 1, 2, 3, 4, 5. And here, thankfully, we don't have to worry about midpoints. We don't need to worry about that subtracting the 0.05 from each and adding it to the next. Remember that? I don't even remember what it's called. It's so little used. Okay, so those that scored a 1 go up to, say, 0.16, which might be a little bit higher than the 0.15. And then the 2, those that scored a 2 went up to 0.22. Those that scored a 3 went up to almost the 0.30 there, okay? And then those that scored the 0.2, or those that scored the 4, we had a probability of 0.2 right there. And then as far as the 5, we've got 0.14. Okay, so that is then what the that's what the histogram looks like for that particular data set. Now, we would not be able to construct that if we did not actually have a discrete probability distribution, okay? So we don't need to do the try it yourself too, okay? Just remember that these numbers here along the y-axis are the relative frequency. That is the frequency divided by the total number of, say, people polled, okay? That is your relative frequency. That is what we are looking for the y-axis, okay? Easy enough. And this is actually a pretty symmetric bell-curved data set, okay? As you can see, remember all of our bell curve and skewed left, skewed right distribution, okay? So example 3, verifying probability distributions, okay? It says verify that the distribution at the left on page 193 is a probability distribution. So they give us already the probability in decimals. So in other words, the probability P of X is already the relative frequency. So if you need to determine whether that is actually a probability distribution, we would add those up to see that they do in fact equal 1. And then of course, we need to make sure that none of those relative frequencies are greater than 1, and they're not. Okay? So, let's see. For identifying probability distributions from example 4, okay? So again, for example 4, 1, you've got X here, and you've got P of X, and of course, since these are already decimals, we don't need to worry about the relative frequency. It's already been done for us. So these numbers right here, in P of X, the probability, that is what's important, okay? We add those up to see if they equal 1. The first condition that all of them are between 0 and 1 has already been verified. So none of them are greater than 1. So now all we need to do is add them all together. And when we add all of those together, that equals 1.07. So that should tell you that that is not a normal probability distribution, because those probabilities are greater than 1, and that's breaking the rule. Or not greater than 1, that they don't add up to equal 1, my fault, sorry. Okay, so if we look at table 2, we have that X is 1, 2, 3, and 4, and our probabilities are, I'm going to do decimals where I can, 0.5, 0.25, 5 over 4, which is 1.25, and -1. Well, remember that these probabilities can only be valid if they're between 0 and 1. So this one here, greater than 1, that one there, less than 0. So that is not a probability distribution either. So let's look at the try it yourself. Okay, the try it yourself 4, we have our X values here, 5, 6, 7, and 8. And the probability here is 1/16, which as a decimal is 0.0625. And of course, I didn't allow myself enough space. Why would I? And then 5/8 is 0.625. And 1/4 is 0.25. and 1/16 again is 0.0625. So we are going to add all of those up together. So 0.0625 plus 0.625 plus 0.25 plus 0.0625. And that equals, let me check it again just to make sure, 0.25 plus 0.0625. That equals 1. Okay, so that is a probability distribution table because none of the probabilities are less than 0 or greater than 1, and the sum of them equal 1. Okay, so far, easy enough. Now, this next thing is a little bit trickier, okay? We are finding the mean of a probability distribution. This is going to lead to one of those tables that we used, that we had to find the mean and then the squares and then the sum of the squares and all that. That we're getting towards that. Okay, now in order to find the mean, and we are on the top of page 194, the mean formula is given as the sum of x times p of x. In other words, the x value times the probability and then adding all those together, okay? So we're looking at example 5. This is the table. So we'll work through this. So 1, 2, 3, 4, 5. We're given this information in this table. Of course, we will not be given this information in all the tables. We would need to find this ourselves, okay? But we're using an example, this data from an earlier example. So here's our x times p of x. Well, x comes from that column, okay? So it's 1 times 0.16, and then 2 times 0.22, 3 times that probability, 4 times its probability, and 5 times its probability. So you would pull out your calculator and you will do all of these calculations, okay? So 0.44, 0.84, 0.80, and 0.70. And then you'll add all of those up together and you get that the sum of those is 2.94. That is the mean of a probability distribution. It is nothing at all like finding the mean of a regular, quote unquote, regular data set. Not even close, okay? That is the mean. You have to take the x value times the relative frequency, which is the probability, and then add all of those products together. Now that is going to be used to get us into the variance and the standard deviation, okay? So now what we're doing is we are looking at example 6, okay? Now, so what I'm gonna do is so we're gonna write the mean up at the top here, 2.94, and I'm gonna use this same table, but just erase some of this so we can extend this table to find the variance and the standard deviation, okay? So we will extend this table. So what we've got then would be our x value minus that mean, okay? Then, remember, we've got the squares, okay? And in this table, we're not going to take the sum of the squares. we're just going to take each one of those squared values and multiply it by the relative frequency, the probability column, okay? So the first thing that we are going to do is take x, so that would be 1 minus our 2.94. That is what goes into this math right there. Then it would be 2 minus the 2.94, etc. Okay? So what we're going to do is 1 minus, so let's make sure, 1 minus, they're using 2.9, okay, so we'll use 2.9, or no, they're using 2.94, and that's good, that's good. So 1 minus 2.94 is negative 1.94. So on your calculators then, you would immediately hit the square button, okay? And that number then will carry into the last column, and we're going to multiply that by the probability. So this is how this whole entire remainder of this table is going to work. 2 minus 2.94 gives you negative 0.94. And when you hit your square button on your calculator, and then you will carry that over and multiply that by the 0.22. Okay, so all the way across. So what I'm going to do now is just copy down the table so we can do the work mathematically from this. 0.0036, because all of this is just calculator work, okay? Now that I've explained to you how to find this column here, it's your X column minus your mean, okay? And then square it to get the next column, okay? And then we are going to bring this over here and multiply by the probability. So this last column is the one that's important. This is the one that's important. This is going to be the column from which we find our variance and then our standard deviation. So doing all of this multiplication, okay, one at a time, changing colors, okay, would give us the 0.602176, 0.194392, 001008. This is very sloppy. I'm looking at my book as I'm writing. And then 0.594104. Okay, so now that you've got all of these products down here, okay, now what we're going to do is add them together, okay? And when we add all of those together, we get 1.6164. That is our variance, okay? Now remember, the standard deviation is to take the square root of that. So the standard deviation is 1.3, okay? That is what we are looking for. So the interpretation of that is that most of the data values differ from the mean. In other words, that's the distance they are away from the mean by no more than 1.3 standard deviations. Okay, so that is a big, long ordeal. But if you remember how to get through this table by just following what the top of the table tells you to do, it's not a bad process. It's long and it's tedious. It's a lot of calculator work. Thank goodness we've got the calculators. So the last thing is the expected value, which I believe for right now we'll just forego. Okay, so as far as the homework problems that I am giving you for 4.1, okay, and there's no expected value problems in this homework section, like at all. Not that they're not even there. We're doing 10, 12, 14, 16, 19, 21, 23, 26, 28, 30, and 32. And actually, it is very, very simple. Okay. Talk to you later. 4.2 is next. See you guys.